Yeah, this is fine. You want to keep the oxidizer separate from the reducer. And this is fine. The electrons are going to originate from the reducing agent and go to the oxidizing agent. That's fine too. And so there's no problem with this, the way it's designed, except by convention. You know, it doesn't matter if it's left to right or right to left. It's all relative, but convention dictates that we have the electrons move left to right. If we have the electrons move left to right, then we should put the reducing agent on the left. But we can be more specific here. What is the reducing agent? Zinc. And so what we're going to do is we're just going to put the zinc metal here. This is the reducing agent. And label it. How does the reducing agent work? Well, zinc is going to lose 2 electrons to form zinc ion and 2 electrons. Where are those 2 electrons going to go? The 2 electrons are going to be fed in the wire. So the 2 electrons are going to come this way, and then the Zn2 plus is going to go out into. So we'll need something for the Zn2 plus to go into. What do we need to help stabilize we need a liquid like water. Just have water here. Otherwise, if the zinc ions just go into air, then we don't form that, that sphere of water molecules around the zinc to help stabilize it. Do you recall what that sphere of water molecules is called that helps stabilize the zinc ion? Or any ion? Do you have it? It starts with high, yeah, high. Chapter 14, I guess it was chapter 15. No, chapter 16, all right. Chapter 16. Yeah, hydrated ion or hydration sphere. We need we need water to help hydrate the zinc to make it more stable. So here's some copper ions that are hydrated. The zinc would be the same thing. Put the zinc there, put a sphere of water molecules to help stabilize it. Otherwise, if it's just in air, it's not going to happen. It's going to be totally unstable in air. And so this is why we need a liquid here. Otherwise, we wouldn't need a liquid. We need a liquid so we can make Zn2 plus aqueous, which is going to be a heck of a lot more stable than just Zn2 plus in air or Zn2 plus in the gas phase. But the electrons aren't going to go in the water. The electrons are going to be fed out through the copper wire. But something's got to be pulling the electrons, because if the zinc just give up electrons, it said, here, take these electrons. No, something has to oxidize the zinc. And so what is oxidizing the zinc? Copper. Well, here we have to feed electrons to copper. In fact, what's oxidizing the zinc is copper 2 ions. The copper 2 ions, this is going to be in solution as well. And so we need something to feed the electrons to the copper 2. Well, what can I use to feed the electrons to copper 2? Can I use zinc to feed the electrons? So for example, if I made this out of zinc here, yeah, that would work. The zinc could supply it. This is called an electrode. The electrode feeds the electrons to the oxidizer here.
That would be direct contact.
But it would be direct contact. I need something that copper 2 will not attack. Give me a metal that copper 2 will not attack. Copper. And so if I make this out of copper, then copper 2 is not going to attack it. It's just going to feed off the electrons, but those electrons are not coming from the copper. The electrons are coming from the zinc. And so here, the copper, the 2 electrons are going to go here. And we're going to deposit copper metal on this electrode. So this electrode is going to get deposits of copper formed. This electrode is going to be eaten away. So pretty soon this electrode starts getting smaller and smaller. As this reaction takes place, electrode gets eaten away. Whereas as reaction takes place here, a fuzz develops on this electrode, which is copper metal precipitate. And so at this electrode, copper 2 plus 2 electrons goes to copper solid. So this is also called an electrode because the electrode is feeding the electrons over from this side to the other side. And we give names to these electrodes. For example, this electrode is called the what were the two names we give electrodes? We can call it either a starts with the C. It's AC. I don't know if anybody caught it, but I called it AC. AC. Alphabetical. This is why I go left to right, so it's easier to remember. AC.
What chapter is this?
19. This is right at the beginning of 1921.
Oh, and it's cathode.
Yeah, we call it the anode and the cathode. In fact, that's how this is labeled. Anode beaker, cathode beaker. And so the anode, this is just by convention. Anodes are typically written for voltaic cells and batteries. Anodes are typically written on the left. That way electrons flow left to right. Where did the name anode come from? Anions. And what's the significance of the anions?
Because
Well, one thing that's going to stabilize this zinc 2 plus is having the water hydrations. But that's not enough because water is neutral overall. It's just that delta minus that's helping stabilize it. If we're generating cations without any anions, can I have a bottle of, let's say I'm on a low sodium diet. And I want the salt without the sodium. Just give me the chloride, no sodium. Can you get the chloride without the sodium in sodium chloride? Is that possible? No. You have to take, unfortunately, you have to take both. And so the same thing here, we're just generating zinc 2 plus, but that's going to be impossible to do, sustained. You can generate a little bit because the waters will help stabilize it. But if you try to generate a lot, then you're going to be in trouble. You're going to be in trouble because there's no... Have you ever been shocked? Obviously, I think everybody's been shocked by static electricity. Well, the amount of static electricity that this is generating is horrendous. If you continue to do this, there's so much static electricity here, you'd have a huge lightning bolt from this. You can't have this much voltage, this much potential, this much positive charge without being in big trouble. And so what's going to happen is it's going to stop. The battery's going to stop.
what's the reason for the salt bridge?
The salt bridge is to make sure that we maintain electrical neutrality.
So that the electricity doesn't build up?
And so we're going to use any salt. So for example, they're using potassium sulfate. So the sulfate over here is going to help stabilize it. So for every Zn 2 plus that's generated, one sulfate has to come in here. Well, how do I get sulfate to come here? How do I get the sulfate to come here? Well, potassium ions don't want to come here. Why?
It's already positive.
It's already positive. Well, how can sulfate leave potassium sulfate? It can't, unless two potassiums leave at the same time. Each sulfate leaves. And so this we call a salt bridge. The salt bridge is to maintain electrical neutrality. And so these are the parts of the voltaic cell that we need. The other thing over here is that we're losing copper 2s, but we aren't losing the nitrates. So for every copper 2 we lose, the 2 nitrates are alone. That's not sustainable. And so for every copper 2 that leaves, 2 potassium ions have to come and take its place. This is salt bridge. And so the other thing you need to know is that oxidation occurs at the anode. What occurs at the cathode? Reduction. And the oxidizing agent is at the cathode. The reducing agent is at the... And the net reaction here, the net reaction that we're using for this battery is Zn2 solid plus Cu2 plus yields Cu solid plus Zn2 plus. There's driving force for this. We say the driving force is this. We're going from a stronger reducing agent to a weaker reducing agent. And we're going from a stronger oxidizing agent to a weaker oxidizing agent. However, that's what we call qualitative. There's a quantitative driving force for this. The quantitative driving force is the volts. And the quantitative driving force for this is 1.1 volts. Volts is like the pressure on the electrons. It'd be like water pressure here, but it's being pulled. You know, water is being pushed through the pipe. However, electrons are being pulled through the pipe. And this is the pipe. And so the volts is the pull on the electrons minus the resistance. And so it's a net tug of war here. So this is being pulled through by 1.1 volts in the battery.
Wait, how do you know it's 1.1?
How do I know it's 1.1?
Yeah.
You just measure it. You measure it. Here. This next figure. This is how I know it's 1.1 volt. You put a voltmeter here and you measure it. It's 1.1 volt. There's easier ways of doing it.
The fuzz that you were talking about that produces some oxidizing agent, is that like the battery acid that goes on a battery hydrogen fuel? Is that the same thing, or is that something completely different?
The battery acid in a car battery?
Yeah, I guess that's a good example. Like the white stuff that gets like when it's getting kind of old, or you find a battery in a remote that's like all blown up and.
Then that white fuzz on there. The white fuzz is a metathesis reaction. That white fuzz is lead sulfate precipitating out. That's what the white fuzz is. And so that's due to metathesis, other things as a side product. But lead sulfate is also part of that battery. We look at car battery reactions shown here. Let me show you. Next on one of these slides. This is it. And so the car battery is actually a pretty complicated reaction. Over here, the cathode in car batteries, solid lead-4 oxide. Lead-4 being a good puller of electrons. So this is the cathode of the oxidizer. The oxidizer can be reduced. This is the anode with the lead. And what it forms is this. There's sulfate present. This is the battery acid, which is also the electrolyte. And what forms is lead-2 sulfate. It's one of the products of that particular reaction. There's going to be some lead-2 sulfate, which is a white insoluble solid precipitate. You want to know, If we do this, what you want to do is you just want to understand the operation of how a battery works, you know, what's happening here. And then should we get it? All right, we're out of time, so I guess we'll stop here.